What if everything you knew about time was flipped upside down? Picture a world where flames don't burn, they unburn, where spilled milk flows back into the glass, perfectly undisturbed. This isn't some twisted dream or a scene from a sci-fi movie. It's a real possibility that the laws of physics actually allow. So why don't we live in that backward universe? Why does time stubbornly move in only one direction forward, carrying us along like an unstoppable river? The answer lies in the very fabric of reality itself, woven into the moments after the Big Bang and echoing through the cosmos in ways that still baffle the brightest minds. Think about the last time you watched a candle melt. The wax drips, the flame flickers, and the smoke curls upward, all of it unfolding in a sequence that feels inevitable. But here's the twist: the equations that govern physics don't actually care which way time flows. They work just as well backward as they do forward. So why does the universe have a favorite direction? The secret might be hidden in something as simple as a shattered teacup. When it breaks, the pieces scatter in a way that's easy to see but impossible to undo. That irreversibility, that one-way ticket from order to chaos, might hold the key to time's relentless march. From the explosive birth of the cosmos to the mysterious depths of black holes, time's arrow points in ways that shape everything from the fate of stars to the beating of your own heart. And the deeper we dig, the stranger it gets. Could time's forward motion be tied to the very nature of existence? Could it be the reason we remember the past but not the future? In this video, we're going to unravel these cosmic riddles, exploring the science that explains why time flows the way it does, and what that means for the universe, for history, and even for you. This isn't just a story about physics. It's a story about why reality works the way it does, and by the end, you'll never look at a ticking clock the same way again. To understand why time only moves forward, we have to talk about entropy, a concept so fundamental that it shapes everything from the universe's grandest structures to the tiniest interactions in your morning coffee. Think of entropy as nature's way of keeping score. Every time energy disperses, every time heat spreads, every time a system becomes more disordered, entropy increases. And here's the crucial part: it always increases. That's the second law of thermodynamics in action, and it's the reason shattered glass doesn't reassemble itself and why you can't unscramble an egg. But why does entropy only grow in one direction? The answer takes us back to the very beginning, the Big Bang. Our universe started in an incredibly ordered, low entropy state, a speck of unimaginable density and heat. As it expanded, that order began to unravel. Particles spread out, energy diffused, and chaos took hold. That initial moment of cosmic symmetry was like winding up a clock. Once released, the gears could only turn one way. Every event since, from the formation of galaxies to the rustling of leaves, has been part of that unstoppable march toward greater disorder. This isn't just about broken teacups or melting ice cubes. Entropy shapes time itself. Black holes, for instance, are entropy powerhouses, devouring matter and radiating energy in ways that further tilt the cosmic scale toward chaos. Even your own body obeys this law. Every heartbeat, every thought, every chemical reaction in your cells contributes to the universe's growing disorder. And that's the profound irony. The very processes that sustain life also nudge the cosmos closer to its eventual heat death, a distant future where energy is so evenly spread that nothing meaningful can happen anymore. Yet this raises another mystery. If the laws of physics don't care about time's direction, why did the universe start with such low entropy in the first place? Some theorists suggest there might have been a before the Big Bang, a hidden epoch where time flowed differently. Others propose that our universe is just one bubble in a vast multiverse, each with its own arrow of time pointing in unpredictable directions. But for now, one thing is certain. As long as entropy keeps increasing, time will keep moving forward, dragging us all along for the ride. Imagine holding a deck of cards fresh from the box, perfectly ordered, every suit in sequence, each card pristine. Now shuffle it. The deck becomes disordered, random, chaotic. That's entropy in action. But here's what's fascinating. You'd never expect a shuffled deck to spontaneously reorganize itself back into perfect order. That's the universe's unspoken rule: disorder only grows. And this isn't just about cards or spilled milk. It's the reason time has a direction at all. Take a moment to watch steam rise from a cup of tea. Those swirling tendrils don't just hover in place. They spread out, dissipating into the air, never to return to the cup as boiling water. This irreversible dance is entropy at work, and it's happening everywhere, from the vast expanse of galaxies to the chemical reactions in your cells. Even something as simple as a campfire tells the story. The logs burn, releasing heat and smoke, transforming into ash. The energy disperses, the molecules scatter, and the system becomes more disordered. The reverse, ash spontaneously reforming into wood, is so unlikely that it might as well be impossible. But why does the universe play by these rules? Why did it start with such an improbable state of order, like that pristine deck of cards? One theory points to the Big Bang as the ultimate reset button. In those first fleeting moments, the cosmos was a searing hot soup of particles, unimaginably dense and uniform. That uniformity meant low entropy, a state of extraordinary order. As the universe expanded and cooled, that order began to unravel, like a tightly wound spring finally releasing its energy. Every galaxy born, every star that ignited, every planet that formed was another step toward greater disorder. Some scientists speculate that this initial low entropy state might not be a coincidence at all. What if our universe is just one bubble in an endless cosmic foam, part of a multiverse where each pocket has its own arrow of time? In some, entropy might decrease, making time flow backward from our perspective. In others, time could loop or even stand still. But for us, here and now, the arrow points forward, driven relentlessly by the growing chaos of the cosmos. Yet, even with all we've uncovered, the mystery deepens. If entropy always increases, why do we see pockets of order, like planets, life, even conscious beings emerging from the chaos? The answer lies in the way energy flows. Stars convert hydrogen into helium, creating pockets of complexity amid the universe's grand slide into disorder. Life itself is a temporary rebellion against entropy, a fleeting eddy in the cosmic stream. But even these islands of order must pay their debt to chaos, eventually succumbing to the universe's relentless tide. So the next time you see a shattered glass or feel the warmth of sunlight on your skin, remember, you're witnessing the engine of time itself. Entropy isn't just a scientific concept, it's the silent force that shapes our reality, weaving the past, present, and future into a story that can only move forward. And somewhere in the distant reaches of space and time, the universe keeps its ultimate appointment, a state of perfect, unchanging disorder where time itself may finally lose its meaning. The Big Bang wasn't just the beginning of our universe, it was the ultimate cosmic reset button, wiping the slate clean with a level of order so precise it defies imagination. Picture a single point, hotter and denser than anything we can recreate, where all the energy and matter of the cosmos were packed into a space smaller than an atom. That's the low entropy seed from which everything grew. In those first moments, the universe was almost perfectly uniform, a sea of particles so tightly arranged that entropy, the measure of disorder, was incredibly low. This wasn't just a tidy starting point, it was the fluke that made time's one-way street possible. But how did such an improbable state come to be? If entropy always increases, why did the universe begin with this fleeting moment of near-perfect order? One compelling idea points to quantum fluctuations, those tiny, unpredictable jitters in the fabric of reality. In the chaotic froth of the early cosmos, these fluctuations might have tipped the scales, creating a pocket of ultra-low entropy against all odds. It's like shaking a box of puzzle pieces and having them land perfectly assembled, a stroke of cosmic luck so rare it might only happen once in an eternity. Another possibility is even more mind-bending. Our universe might be just one bubble in an endless multiverse. In this vast foam of realities, each with its own laws of physics, some universes could have started with high entropy, their time arrows pointing sideways or even backward. Ours, by sheer chance, got the golden ticket, a low entropy beginning that set the stage for stars, planets, and life itself. But this raises another question. If the multiverse is real, could there be places where time runs in reverse, where smoke pours back into fires and eggs unscramble themselves? The math allows it, but we've never seen it. What makes the Big Bang's low entropy state so puzzling is that it breaks the rules of probability. In any system left to its own devices, disorder tends to grow. So why did the universe start in a state that's astronomically unlikely? Some theorists suggest gravity might hold the answer. In the early cosmos, gravity's pull could have acted like a cosmic organizer, clustering matter into galaxies and stars, temporarily creating pockets of order even as the universe as a whole became more chaotic. It's as if nature found a loophole, using gravity to carve out islands of structure in a sea of growing entropy. Yet the deeper we dig, the more questions arise. Could the Big Bang have been a rebound from a previous universe's collapse, a cosmic cycle of order and chaos playing out over eons? Or was our low entropy beginning the result of some deeper, undiscovered law of physics? For now, these mysteries linger at the frontier of science, reminding us that time's arrow and the universe itself is far stranger than we once thought. And every clue we uncover only tightens the grip of the ultimate riddle. Why did time start moving forward in the first place? Quantum mechanics paints a picture of reality so bizarre that even time itself seems to wobble. At the tiniest scales, particles exist in a fog of possibilities, simultaneously occupying multiple states until the moment they're measured. An electron isn't just here or there, it's both and neither until observation forces it to choose. This blurring of potential and actuality makes the quantum realm seem timeless, where past and future lose their grip. Yet here we are, stuck in a world where spilled milk never leaps back into the glass. How does this microscopic chaos resolve into the steady, one-way flow of time we experience every day? The answer might lie in a phenomenon called decoherence, the universe's way of turning quantum weirdness into everyday certainty. Imagine a room full of whispering voices, each representing a possible state of a particle. Left alone, these whispers overlap into a meaningless buzz. But the moment someone shouts a question, the equivalent of a measurement, the voices snap into a single, clear response. Decoherence is that shout, the process by which quantum possibilities interact with their environment, collapsing into the definite outcomes we perceive. Every photon hitting your eye, every atom bumping into air molecules, chips away at the quantum fog, forcing reality to pick a lane. This doesn't just explain why we don't see cats both dead and alive. It's the bridge between the quantum realm's timeless dance and the stubborn forward march of time. The more a quantum system interacts with its surroundings, the more its countless possibilities bleed away, leaving behind the orderly, irreversible chain of events we call the past. Think of it like a drop of ink in water. At first, the ink hovers in a concentrated blob full of potential paths, but as it spreads, those possibilities vanish into the uniformity of the liquid. There's no going back, just like time itself. Yet here's the twist: decoherence doesn't just create the arrow of time, it's also shaped by it. The universe's low entropy beginnings set the stage for decoherence to unfold in a particular direction. In those early moments when particles were densely packed, interactions happened fast and furiously, stamping out quantum ambiguity like a cosmic game of whack-a-mole. As the cosmos expanded, decoherence kept pace, weaving randomness into the tapestry of cause and effect. Without this process, time might have no direction at all, just a jumble of overlapping possibilities, like a movie played backward and forward at once. But decoherence alone can't explain everything. Why does time's arrow point the same way for all of us? Why don't we see pockets of reality where entropy decreases, or where quantum superpositions persist at macroscopic scales? Some physicists speculate that gravity, the great unifier of cosmic forces, might play a role, acting as a kind of timekeeper for the universe. Just as gravity sculpts galaxies from the primordial soup, it could also nudge decoherence toward a consistent flow, aligning countless quantum events into the single timeline we experience. The deeper we probe, the more entangled time becomes with the fabric of reality itself. Quantum mechanics suggests that at its core, the universe might not even distinguish between past and future. Yet somehow, from this timeless sea, our lived experience emerges a relentless, one-way journey from memory to anticipation. Decoherence is the mechanism, but the why remains one of physics' greatest puzzles. Perhaps time's flow isn't just a feature of the universe, but a consequence of how we, as observers, interact with it. After all, without someone to remember the past or anticipate the future, would time have any meaning at all? So the next time you check your watch, remember, those ticking seconds aren't just marking moments. They're the echoes of quantum possibilities settling into history. A cosmic chain reaction that began at the Big Bang and continues in every atom, every thought, every heartbeat. The universe insists on moving forward, even if its smallest pieces can't quite decide which way is up. Black holes aren't just cosmic vacuum cleaners, they're time machines that twist reality to its breaking point. Picture an astronaut drifting toward a black hole's event horizon, the point of no return. From Earth's perspective, something bizarre happens. The astronaut's movements slow to a crawl, their image stretching and reddening as if frozen in a single moment. Yet for the astronaut, time flows normally until the crushing grip of gravity tears them apart. This isn't science fiction. It's Einstein's general relativity in action, revealing time as a fluid, stretchable fabric rather than a rigid clock. What's really happening here? Gravity doesn't just bend space, it warps time itself. Near a black hole, gravity is so intense that time slows dramatically compared to distant observers. This effect, called time dilation, means a minute near the event horizon could equal years or even centuries elsewhere. The closer you get to the black hole's edge, the more extreme the distortion becomes, like a cosmic version of Zeno's paradox where you never quite reach the finish line. For the outside universe, the falling astronaut becomes a fading snapshot, a ghost trapped in the last second before oblivion. But here's where it gets stranger. Black holes don't just bend time, they might also shred the very rules that govern it. Entropy, the universe's relentless drive toward disorder, relies on information, the record of how particles move and interact. Yet black holes famously swallow information whole, leaving no trace of what fell in. This information paradox suggests these cosmic monsters might erase entropy's paper trail, scrambling the universe's accounting system. If entropy defines time's arrow, could a black hole's appetite for data somehow bend or even reverse it? Some theories propose wild answers. The holographic principle suggests that all the information swallowed by a black hole isn't lost, it's smeared across its event horizon like a cosmic thumbprint, encoded in 2 dimensions rather than 3. If true, time near a black hole might not just slow down, it could become a scrambled echo of itself, a hall of mirrors where cause and effect blur. Even more radical is the idea of white holes, theoretical opposites of black holes that spew out matter and energy. Could these be the exit doors for time-reversed universes, where entropy runs backward and shattered teacups reassemble themselves? Yet for all their mystery, black holes might also hold clues to time's deepest secrets. Their singularities, points of infinite density, are where our current laws of physics break down entirely. Here, Einstein's relativity clashes with quantum mechanics, and time itself might cease to have meaning. Some models suggest that inside a black hole, space and time swap roles, making the singularity not a place in space but a moment in time. Falling in wouldn't just mean moving toward a point. It would mean hurtling toward an inevitable future, like a train locked on rails. The paradoxes pile up, but one thing is clear: black holes are time's ultimate stress test. They stretch, freeze, and perhaps even erase the flow of causality we take for granted. And as we peer into their inky depths, we're forced to ask, is time's arrow truly universal, or just a local quirk of our corner of reality? The answers might rewrite not just physics textbooks, but our very understanding of existence itself. Your memory is a time machine, but one that only moves in reverse. Every recollection, from your first bike ride to yesterday's coffee, stitches together the story of your life. Yet here's the puzzle: why don't you remember the future? It's not just that you can't, it's that the very idea feels absurd. This isn't a limitation of your brain, it's a clue to how consciousness dances with the universe's deepest rhythms. Think about the last time you watched a video in reverse. Water leaps back into a glass, shattered porcelain reassembles. It feels unnatural because your brain is wired to expect entropy's rise. Your perception of time isn't just a passive recording. It's an active construction, shaped by the same forces that dictate why eggs don't unscramble themselves. When neurons fire in your brain, they leave trails, physical changes that become memories. But these trails only form in one direction, echoing the universe's relentless slide toward disorder. This alignment between mind and cosmos goes deeper. Consider déjà vu, that eerie sense of reliving a moment. Some scientists suggest it might be a glitch in your brain's time labeling system, a fleeting confusion between past and present. Normally, your hippocampus stamps memories with temporal markers, creating a mental timeline. But when entropy's arrow is reflected in your brain's chemistry, those markers can blur, offering glimpses of how fragile your perception of time really is. What if consciousness itself is a byproduct of entropy's march? The integrated information theory proposes that conscious experience arises from complex networks, like your brain processing information in highly ordered states. As entropy increases, these systems work harder to maintain coherence, generating the flow of subjective time. In other words, you perceive time because your brain is fighting chaos, weaving order from disorder like a loom threading randomness into narrative. Yet mysteries remain. Patients with rare brain injuries sometimes experience chronostoses, where time seems to stutter or loop. Others lose the ability to sequence events entirely, living in a perpetual present. These disruptions hint that time's arrow in the mind isn't just about physics, it's biology, neurology, and something profoundly existential. Your memories aren't just records, they're the universe's way of giving entropy a voice, turning cosmic disorder into stories that make sense. So when you recall a childhood birthday or plan tomorrow's meeting, you're not just observing time's flow, you're participating in it. The past feels solid because entropy has cemented those moments into history. The future feels open because the universe hasn't decided yet. And you, perched between memory and anticipation, are the universe's way of bearing witness to its own unfolding. Flip a coin and the physics describing its spin works perfectly whether you watch it forward or backward. The equations governing atoms, light, even gravity, they don't care which way time flows. On paper, there's no reason a shattered glass couldn't reassemble, its shards leaping back onto the table in perfect formation, yet we never see it happen. This paradox, the symmetry of microscopic laws versus the stubborn one-way street of our everyday experience, is one of physics' greatest puzzles. Take Newton's cradle, those swinging steel balls that click back and forth. Film them in motion, then play the footage in reverse. You wouldn't be able to tell the difference. The collisions look identical either way. That's time's symmetry in action. Zoom in close enough, and particle interactions share this property. A collision between two electrons obeys the same rules whether time runs forward or backward. But zoom back out and the illusion shatters. Smoke never pours itself back into a cigarette. Perfume molecules don't retreat into their bottle. The disconnect hints at something profound. Time's arrow isn't written in the laws themselves, but in how countless particles conspire to create the world we recognize. Imagine a box filled with gas. At the molecular level, each particle zigs and zags, bouncing off walls and one another in perfect accordance with time's symmetric laws. But collectively, they behave predictably. The gas spreads evenly, never spontaneously bunching into a corner unless forced. This leap from reversible chaos to irreversible order is called the statistical arrow of time. It's not that individual particles disobey the rules, it's that the odds of trillions of them arranging themselves into a more ordered state are vanishingly small. A single water molecule might by chance move against a current, but an entire river reversing flow, that's the universe playing against impossible odds. Yet statistics alone can't explain why time had a direction in the first place. Enter the past hypothesis, the idea that our universe began in an ultra-ordered, low-entropy state, setting the stage for everything that followed. Like a deck of cards freshly unboxed, the Big Bang dealt reality a hand so improbably neat that any shuffle could only make it messier. This initial order didn't just nudge time forward, it locked the door behind it. Even if individual particles could reverse course, their collective dance had nowhere to go but toward greater disorder. Some theorists take this further, suggesting emergent phenomena, like consciousness or weather patterns, might forge new arrows of time within the larger flow. A whirlpool in a river has its own local currents, yet still moves downstream. Could our perception of time be like that whirlpool, a self-contained rhythm spun from deeper cosmic tides? The math allows it, but the mystery lingers. Why does the universe insist on playing the film in one direction when the projector works just fine in reverse? Perhaps the answer lies in the spaces between the equations, not in the rules themselves, but in how we, as observers, stitch them into a story. After all, without memory, without entropy, without cause and effect, would time have any meaning at all? The laws of physics might be blind to its flow, but we're not. We're the universe's way of bearing witness to its own unfolding, one irreversible moment at a time. Cause and effect seem as fixed as the ground beneath your feet. Drop a ball and it falls, strike a match and it ignites. But peel back the layers, and this bedrock principle starts to look more like a symptom than a law. Why must causes always come before effects? The answer might lie in entropy's silent choreography. Picture a row of dominoes falling in perfect sequence. The chain reaction feels inevitable. One tip leads to the next, but film it in reverse, and the dominoes appear to defy logic, standing upright as if by magic. The difference isn't in the dominoes themselves, it's in the hidden hand of entropy, ensuring energy disperses rather than concentrates. Now imagine a world where effects precede causes. A fire erupts and seconds later, someone strikes the match that started it. Your alarm clock rings at 7 a.m., prompting you to set it the night before. This isn't just backward, it's a reality where memory and anticipation swap places. The reason such scenarios feel absurd traces back to the universe's low entropy beginnings. In a high entropy state where energy is evenly dispersed, events could unfold in any order. But our universe started with a lopsided distribution of order, creating a gradient that only allows time to flow one way. Causes must precede effects because entropy's rise acts like a cosmic traffic cop, directing the flow of events. Quantum mechanics adds another wrinkle. At the smallest scales, particles don't always play by causality's rules. Virtual particles pop in and out of existence, seemingly uncaused. Entangled particles influence each other instantaneously across vast distances, as if effect ignores cause entirely. Some interpretations suggest that at the quantum level, time might not have a fixed direction. Events could influence the past just as easily as the future. But zoom out and decoherence kicks in, smoothing these quantum quirks into the orderly cause and effect world we know. It's like watching a chaotic crowd suddenly fall into step. Individual randomness gives way to collective direction. The link between causality and entropy runs even deeper. Consider a cup of coffee cooling on a table. The heat flows from the cup to the air because the universe prefers dispersed energy, higher entropy. But this transfer also defines the arrow of causality. The hot cup causes the air to warm, not the other way around. Reverse the entropy, and you'd see warm air spontaneously heating the coffee, rewriting causality itself. This symmetry breaking is why time's arrow and cause and effect are two sides of the same coin. One can't exist without the other. Yet here's the twist: causality might be more flexible than we think. In certain quantum experiments, particles seem to decide their properties retroactively, as if future measurements influence past states. These delayed choice experiments suggest that at some level, the universe doesn't rigidly enforce cause before effect. It's as if time's arrow is a macro-scale illusion, a statistical certainty that emerges from countless tiny, directionless interactions. So is causality fundamental or just a side effect of entropy's march? The answer might be both. Like a river carving a canyon, entropy's relentless flow has shaped the channels through which causes must travel. But dig deep enough, and you'll find the bedrock of reality doesn't care which way the water flows, only that it follows the path of least resistance. Causality, then, isn't just a rule of time. It's the universe's way of making sense of itself, one irreversible moment at a time. Cosmic inflation wasn't just the universe's growth spurt, it was the moment time got its marching orders. Picture the cosmos in its first sliver of existence, smaller than a proton but hotter than a supernova. Then, in less than a blink, it ballooned by a factor of a trillion. This wasn't gentle expansion. It was a runaway stretch of space-time so violent that it ironed out every wrinkle, leaving the universe smoother than a pane of glass. But amid this frenzy, something subtle yet monumental happened. Inflation may have handed time its arrow, setting entropy on the path that would define reality itself. Think of it like a snow globe shaken with unimaginable force. Before inflation, the universe was a chaotic swirl of quantum foam, with energy bubbling in random fluctuations. The explosive stretch didn't just enlarge space, it diluted those fluctuations, leaving behind a startlingly uniform sea of matter and radiation. This smoothing effect wasn't just cosmetic, it was a cosmic reset that created the ultimate low entropy starting line. Like a sprinter crouched in perfect readiness, the universe was poised to run in only one direction, toward disorder, yet inflation's role goes deeper. As space stretched, the energy driving it, think of it as a strange, repulsive gravity suddenly decayed, flooding the cosmos with particles and heat. This release was entropy's Big Bang within the Big Bang. The transition from ordered inflation to the messy particle soup was a one-way door. Reversing it would be like unscrambling an egg and then stuffing it back into its shell. The universe couldn't uninflate, just as it couldn't undo entropy's sudden leap. Here's where time's arrow sharpens. Some theories suggest inflation didn't just allow entropy to rise, it demanded it. The vacuum energy powering inflation was a metastable state, like a pencil balanced on its tip. Once it tipped over, there was no going back. This collapse into a hotter, denser universe was the first irreversible act, the domino that set all others falling. From that moment forward, every particle collision, every galaxy's birth, even your own heartbeat, would echo that initial plunge into chaos. But what if inflation wasn't a one-time event? Eternal inflation theory proposes that our universe is just one bubble in an endless froth of inflating space. Other bubbles might have different laws, different arrows of time, or no time at all. In some, entropy could decrease, making time flow backward from our perspective. Yet for us, the die was cast the moment our bubble burst into existence. Inflation's endgame wrote time's rules into the fabric of space, leaving no undo button. The echoes of this epoch are still visible today. The cosmic microwave background, the afterglow of the Big Bang, shows near-perfect uniformity, a relic of inflation's smoothing power. But look closer, and you'll find tiny temperature variations, the quantum seeds that would grow into galaxies. These imperfections are more than cosmic fossils. They're proof that inflation didn't just create space, it curated the conditions for time's relentless flow. Without those subtle flaws, the universe might have remained a featureless void with no structure, no change, and no arrow of time at all. So the next time you glance at a clock, remember, those ticking seconds trace back to a primeval instant when space itself stretched beyond imagination, locking in time's irreversible path. Inflation didn't just shape the universe, it gave time its voice, turning quantum randomness into the story we're all living, one irreversible moment at a time. Was there a before the Big Bang? The question feels like asking what's north of the North Pole, a riddle that twists logic until it snaps. Yet some of cosmology's boldest theories suggest our universe might not be the first chapter in the story. Picture a cosmic seesaw, a previous universe collapsing inward, reaching a point of unimaginable density, then rebounding outward in the explosion we call the Big Bang. In this bounce scenario, time wouldn't begin, it would bend, flipping its arrow as the contraction became expansion. Think of it like a film reel running backward until the final frame, then restarting in forward motion. During the collapse phase, entropy might decrease, making time appear to flow in reverse from our perspective. Stars would unexplode, scattered dust would gather into galaxies, and radiation would concentrate rather than disperse. Then at the moment of the bounce, the cosmic reset button gets pressed, entropy starts climbing anew, and time as we know it begins its relentless march. The universe wouldn't just rebound, it would rewind its own rules. This isn't pure speculation. Loop quantum gravity, a leading contender to unite relativity and quantum mechanics, allows for such a rebound. In this framework, gravity becomes repulsive at extreme densities, preventing a true singularity and instead triggering a bounce. The equations show time persisting through the transition, meaning the before could be more than philosophical musing. Remarkably, this model might leave fingerprints in our universe today. If gravitational waves from the pre-bounce phase survived, they could be hiding in the cosmic microwave background, waiting to be discovered. But the implications are dizzying. If time's arrow flipped during the bounce, does that mean cause and effect reversed too? Imagine a pre-Big Bang civilization sending messages forward into our universe only for us to receive them before they're sent from their perspective. The paradoxes pile up like cars in a quantum traffic jam. Some theorists sidestep this by proposing the arrow doesn't flip at all. That entropy continues increasing through the bounce, making both phases align in time's direction. Others suggest the pre-Bang universe could have had entirely different physical laws, rendering our concepts of time meaningless there. Perhaps strangest of all is the cyclic universe model, where bangs and crunches repeat endlessly. Each cycle begins with near-zero entropy, expands, then contracts over trillions of years, only to rebound fresh. In this view, time isn't linear but circular, with no true beginning or end. The cosmic microwave background might even show bruises from previous universes colliding with ours during inflation, like ghostly fingerprints on the sky. Yet for all their elegance, these theories face a formidable challenge, the second law of thermodynamics. If entropy always increases, how does each new cycle reset to a low entropy state? Some propose that black holes play a cosmic janitor role, swallowing disorder as the universe contracts. Others imagine entropy resetting at the quantum level during the bounce, like a computer rebooting. But until we find observational evidence, perhaps imprints in the distribution of galaxies or anomalies in the cosmic microwave background, these ideas remain beautiful speculation. What's clear is that the Big Bang may not be the ultimate beginning, but a turning point in a much grander saga. Time's arrow might be more flexible than we thought, bending but never breaking, even as the universe itself reinvents the rules. Every tick of the clock could be echoing across cosmic cycles we're only beginning to imagine. Imagine a universe where rivers flow uphill, where trees grow from leaves back into seeds, where people grow younger with each passing day. This isn't just fantasy, it's a real possibility in the multiverse. If our cosmic neighborhood is just one bubble in an infinite froth of realities, some of those bubbles might have time arrows pointing in entirely different directions. The laws of physics don't forbid it, they just don't organize the furniture that way in our particular universe. Take the humble cup of coffee. In our world, it cools as heat disperses into the air. But in a time-reversed universe, warmth would inexplicably gather from the surroundings to reheat the cup. People there wouldn't find this strange. To them, our universe would seem bizarre, like watching a film where gravity suddenly repels instead of attracts. Their memories would work oppositely too. They'd remember future events and experience the past as anticipation. Birth would begin with death, and first kisses would follow breakups in their personal timelines. The real mind-bender comes when considering consciousness in such a universe. Would beings there perceive time as flowing backward, or would their entire psychology adapt to what we'd consider reversed causality? Some theorists suggest their experience might be identical to ours, like two clocks running in opposite directions but both keeping perfect time. The difference would only become apparent if our universes could somehow interact, creating paradoxes that would make time travel headaches seem trivial by comparison. String theory offers another twist, Brainworld's parallel universes separated by higher dimensions where time itself could flow sideways relative to ours. In these realities, cause and effect might operate in directions we can't even visualize, like shadows trying to comprehend three-dimensional objects. Some brainworld models even allow for time loops, where events circle back endlessly like a record stuck on repeat, no beginning, no end, just eternal recurrence. Yet the multiverse hypothesis raises profound questions. If other timelines exist where entropy decreases, why don't we see evidence of their influence? Quantum mechanics suggests that particles can tunnel between potential realities, so where are the time-reversed particles? One possibility is that the initial conditions of our universe actively suppress such connections, making alternate time arrows as isolated as parallel train tracks running in opposite directions. The most radical interpretation comes from the two-time theory, proposing that some universes might have two temporal dimensions instead of one. In such a reality, time wouldn't be an arrow, but a plane events could unfold in countless directions simultaneously. Beings there might perceive history as a landscape to explore rather than a one-way street, moving through time as freely as we move through space. Whether these alternate timelines exist remains one of cosmology's great mysteries. But their theoretical possibility does something remarkable. It shows that time's forward march isn't an inevitable law of reality, but a peculiar feature of our particular cosmic address. The multiverse doesn't just expand space, it explodes our understanding of time itself, revealing how deeply our experience is tied to the accident of our universe's initial conditions. So the next time you watch steam rise from your coffee or feel the sun's warmth on your skin, consider this. Somewhere in the multiverse's infinite tapestry, those same particles might be dancing to an entirely different temporal rhythm, where heat flows backward, memories unfold in reverse, and the universe whispers its secrets in a language where before and after have traded places. Time crystals sound like something ripped from a sci-fi novel, structures that pulse and oscillate without ever winding down, like a clock that ticks forever without batteries. But these aren't fantasy, they're real, and they're rewriting our understanding of time itself. Unlike ordinary crystals, which arrange atoms in repeating patterns in space, time crystals repeat in time, cycling through states with a regularity that defies the usual rules of energy decay. Imagine a diamond that doesn't just sit on a shelf but dances to its own rhythm forever. The magic lies in quantum weirdness. In 2012, Nobel laureate Frank Wilczek proposed time crystals as a theoretical possibility, systems that break time translation symmetry, meaning they don't behave the same at every moment, even in their lowest energy state. By 2017, labs had created them using chains of ytterbium ions or defects in diamonds, chilling them near absolute zero and nudging them with precise laser pulses. The result, a quantum drumbeat that persists indefinitely, untouched by friction or entropy's usual erosion. Here's what's truly mind-bending. Time crystals don't just ignore time's arrow, they sidestep it entirely. While the universe marches toward disorder, these structures exist in a strange loop, always returning to their starting point like a phoenix perpetually reborn from its own ashes. They're not reversing time, but they're proving that stability doesn't have to mean stillness. A time crystal's rhythm is locked in, immune to the chaos around it, as if it carved out a tiny pocket of temporal defiance. Could this hold clues to controlling time's flow? Not directly, but it reveals that time's rigidity might be more flexible than we thought. If matter can be engineered to cycle independently of entropy's pull, what other temporal rules might we bend? Some physicists speculate that time crystals could simulate exotic states of matter near black holes, where gravity warps time into knots. Others dream of quantum computers using time crystals as error-resistant memory, their unshakable rhythms preserving information against decoherence. Yet the biggest revelation is philosophical. Time crystals force us to ask, is time's arrow truly universal, or just the default setting of our cosmic neighborhood? In a multiverse where entropy rules vary, might other realities host crystals that pulse backward, or in fractals, or not at all? For now, these quantum curios are a whisper from the edge of physics, proof that even time, the most relentless force we know, might have loopholes waiting to be unraveled. Wormholes aren't just cosmic shortcuts, they're potential time machines folded into the fabric of reality. Picture space-time as a sheet of paper, with two distant points brought together by a pencil poking through. That tunnel is the wormhole, a bridge that could let you step across light years in an instant. But here's the twist: Einstein's equations suggest these tunnels might also connect moments in time, not just locations in space. Step in one end, and you could emerge decades or even centuries earlier, like rewinding a cosmic film reel. Yet for all their tantalizing potential, wormholes come with a catch: entropy's unbreakable grip. Even if you could stabilize a wormhole with exotic matter, a hypothetical substance with negative energy, the universe has built-in safeguards. Every action you take inside the wormhole would generate heat, increasing entropy just like stirring cream into coffee. Over time, this buildup could slam the door on paradoxes before they happen. Try to go back and prevent your own birth, and the wormhole might collapse under the weight of its own disorder, preserving causality like a cosmic bouncer. Consider the infamous grandfather paradox. If you traveled back and accidentally prevented your grandfather from meeting your grandmother, how could you exist to make the trip in the first place? Quantum mechanics offers a bizarre loophole: parallel timelines. Some interpretations suggest that wormhole travel wouldn't rewrite history but branch it, spawning a new universe where events unfold differently. In this scenario, entropy still increases overall. No laws are broken, just sidestepped. The original timeline remains untouched, its arrow of time unaltered, while the new branch carries its own version of events. Black holes add another layer of intrigue. Some models propose that wormholes could form from the wreckage of collapsing stars, linking the interiors of two black holes. But here's where entropy flexes its muscles again. The intense gravitational forces near a black hole's singularity would stretch and scramble anything entering it, turning ordered information into chaos. Even if a wormhole survived the process, the sheer disorder at either end might render time travel meaningless, like mailing a letter through a shredder. The ultimate irony: wormholes might exist, but the universe's love affair with entropy could keep them from unraveling time's arrow. Every hypothetical journey through them would leave an irreversible mark, like footprints in wet cement. The cosmos seems determined to keep its chronology tidy, allowing shortcuts through space but guarding the flow of time like a dragon hoarding gold. So while wormholes tease us with visions of ancient Rome or distant futures, they also underscore a profound truth: time's direction isn't just a feature of reality, it's the foundation. Even in a universe riddled with tunnels through space-time, entropy stands sentinel, ensuring that yesterday stays yesterday, and tomorrow remains always just out of reach. Dark energy isn't just stretching the universe, it's erasing it piece by piece. Picture a future so distant that every galaxy beyond our own Milky Way has vanished, not from collapse but from being pushed away faster than light itself. The cosmos becomes an infinite void, with islands of stars disappearing one by one into the darkness. In this lonely expanse, time itself might unravel, not with a bang but with a whimper of heat death, the moment when entropy finally peaks and the universe runs out of usable energy forever. This apocalyptic scenario starts with dark energy's silent dominance. Unlike gravity, which pulls matter together, dark energy pushes space apart with increasing violence. Over trillions of years, it will accelerate the expansion until even the closest galaxies fade from view, their light stretched into undetectable infrared whispers. Civilizations born too late would never know other galaxies existed, their night skies empty of all but a handful of dying stars. The universe becomes a hall of mirrors where every observer thinks they're alone at the center. But here's where time's arrow starts to wobble. In a heat-death scenario, entropy reaches maximum disorder, no more temperature differences, no more energy flows, just a lukewarm sea of particles too dispersed to interact. Without change, without cause and effect, does time even have meaning? A clock can't tick if there's no energy to move its hands. Consciousness couldn't exist in this frozen state, leaving no one to ask what comes next. It's the ultimate paradox. Time might still exist mathematically, but with no events to mark its passage, it becomes as abstract as a calendar with no dates. Some theories offer a glimmer of strangeness in this bleak future. Quantum fluctuations could spawn new, bubble universes in the emptiness, each with its own Big Bang. Time might not end but branch, like a tree growing new limbs from a rotting trunk. Others suggest protons themselves will decay over unthinkable eons, reducing all matter to a thin haze of subatomic particles, a final act of dissolution that resets the cosmic stage. Yet the most haunting possibility is that the heat death isn't an end but a transformation. Black holes, the last structures standing, would slowly evaporate via Hawking radiation, their immense gravity leaking away as faint quantum whispers. The last photon emitted by the last black hole might carry a message from the universe's final moment, a time capsule for no one. In this frozen eternity, even the concept of future dissolves, leaving only the faintest imprint that time once flowed at all. So while dark energy pulls the universe apart, it's also writing time's epitaph. The same force that lets galaxies drift apart may one day render time meaningless, not by stopping it but by emptying it of all events to measure. The arrow that began with the Big Bang could finally rest, its journey complete in a cosmos too cold and quiet to notice. The Boltzmann brain paradox throws our understanding of reality into dizzying uncertainty. Imagine floating alone in an infinite void, your thoughts and memories spontaneously assembling from random quantum fluctuations. No body, no past, no future, just a naked consciousness flickering into existence, convinced it's lived a full life in an ordered universe. This isn't horror fiction, it's a legitimate possibility if entropy fluctuates over infinite time. According to statistical mechanics, even the most improbable events become certain given enough chances. In a cosmos that lasts forever, even a fully formed brain complete with false memories of reading this sentence could pop into being purely by accident. The paradox cuts to the heart of time's arrow. If the universe tends toward disorder, why do we perceive such coherence? One explanation is that we're the fluke. Boltzmann brains, named after physicist Ludwig Boltzmann, should statistically outnumber real, evolved minds in an eternal, fluctuating universe. Every genuine human experience would be drowned in an ocean of phantom consciousnesses, momentary glitches in the cosmic noise. The fact that we observe consistent laws of physics and an unbroken past suggests something's wrong with this picture. Either we're incredibly lucky, or our understanding of entropy's role in time is incomplete. Some theorists sidestep the paradox by invoking cosmic inflation. If the early universe's rapid expansion locked in low entropy, then Boltzmann brains become vanishingly unlikely compared to structured, evolved observers like us. Others suggest the multiverse acts as a filter. Only universes with stable time arrows can support life long enough for beings to ponder the question. But the most unsettling resolution comes from quantum mechanics. If observation creates reality, maybe consciousness itself prevents the universe from degenerating into random fluctuations. A Boltzmann brain couldn't sustain its own existence because the moment it tried to observe its surroundings, the quantum foam would collapse back into chaos. Yet the paradox lingers like a ghost in the equations. Modern cosmology's darkest secret is that statistically, you're more likely to be a momentary hallucination of order than a product of 13 billion years of evolution. Unless, of course, time's arrow isn't just about probability. Perhaps causality is more fundamental than entropy, a thread stitching reality together in ways we're only beginning to grasp. The next time you recall a childhood memory or plan for tomorrow, consider this. The very act of remembering could be the universe's way of proving you're more than just a statistical hiccup in the dark. Loop quantum gravity paints a radical new picture of reality, one where space-time isn't smooth and continuous, but woven from tiny, indivisible threads. Imagine the universe as a cosmic tapestry, each thread a billion times smaller than an atom, knotted together to form the fabric of existence. In this framework, time itself might not flow like a river but tick like a clock, advancing in discrete jumps too small for any clock to measure. This isn't just a tweak to Einstein's relativity, it's a complete overhaul of how we understand time's most basic nature. At the heart of this theory lies the idea of quantized space-time. Just as light comes in discrete packets called photons, loop quantum gravity suggests that moments in time might be fragmented into fundamental units, each a tiny step in the universe's grand timeline. Think of it like flipping through a flipbook. From a distance, the motion looks smooth, but up close, you see it's actually a series of still images. If this model holds, even the most seamless events a falling leaf, a beating heart would be stitched together from these imperceptible time quanta, like frames in a cosmic film reel. But here's where it gets stranger. In loop quantum gravity, time might not even exist as an independent entity. Instead, it could emerge from the relationships between events, like the way temperature arises from the motion of molecules. Picture a symphony where no single instrument plays time. The rhythm only emerges from how the notes interact. Similarly, the universe's clock could be a collective illusion, a side effect of quantum loops intertwining in just the right way. This challenges our deepest intuitions. If time isn't fundamental, why does it feel so inescapably real? The implications ripple outward. If time is granular, there might be a smallest possible unit, a chronon, beyond which division is meaningless. This would place a hard limit on how precisely we can measure intervals, like a cosmic pixel size for duration. Black holes, where gravity warps time to its extreme, could reveal these granular effects. Near a singularity where classical physics breaks down, the discrete structure of time might become visible, like seeing the individual threads in a stretched piece of fabric. Yet loop quantum gravity isn't the only player in this game. Competing theories like string theory approach time's nature differently, treating it as a smooth dimension curled into hidden shapes. The debate hinges on a deeper question. Is time a stage where events unfold, or is it something that emerges from the events themselves? Loop quantum gravity leans toward the latter, suggesting that without change, without those quantum loops rearranging, time would have no meaning at all. This granular view also reshapes entropy's role. If time jumps discretely, does entropy increase in tiny bursts, like a dial clicking upward one notch at a time? Or is disorder itself an emergent property, only visible when zoomed out to our macroscopic scale. Some models even suggest that at the smallest intervals, entropy could briefly decrease, like a cosmic glitch in the matrix, though these fluctuations would be too fleeting and tiny to ever notice. The most tantalizing possibility is that loop quantum gravity could reconcile with the arrow of time. If the universe's initial low entropy state was a result of quantum loops aligning in a highly ordered configuration, then time's forward march might be written into the very geometry of space-time. Every tick of the quantum clock would nudge the cosmos further from that pristine order, weaving the irreversible flow we experience. For now, these ideas remain at the frontier of physics, waiting for experiments to catch up. But if loop quantum gravity is right, time isn't just something we measure. It's something the universe builds moment by moment from the ground up, and that means the ticking clock on your wall might be more than a tool. It could be a window into the stitches holding reality together. String theory whispers of hidden dimensions curled up tighter than a clenched fist spatial folds so small they evade even our most powerful microscopes. These extra dimensions beyond length, width, and depth aren't just mathematical quirks. They could be the secret architects of time's arrow. Picture our familiar four-dimensional space-time as a vast ocean, while these compact dimensions ripple beneath the surface like unseen currents, subtly steering the flow of reality itself. At the heart of string theory lies a radical idea. The fundamental particles we know, electrons, quarks, photons, aren't dots at all, but tiny, vibrating strings. The pitch and resonance of these strings determine their properties, much like how a violin's strings produce different notes. But here's the twist: these strings don't just dance in the four dimensions we experience. They vibrate in 10 or 11 dimensions, their harmonies woven through the fabric of these hidden folds. How might these extra dimensions influence time? One possibility lies in their shape. Just as a twisted garden hose can change how water flows through it, the geometry of these compact dimensions could dictate how entropy unfolds across the universe. If certain configurations allow energy to disperse more efficiently in one temporal direction than another, they'd effectively lock time into a one-way street. Think of it like a hiker descending a mountain. The path up might exist, but gravity makes the downward trek far more natural. Another clue comes from brains, short for membranes, floating in higher dimensional space. Our entire universe might be a three-dimensional brain drifting in a bulk of extra dimensions. Collisions between brains could have sparked events like the Big Bang, imprinting an arrow of time from the very beginning. In this scenario, time's direction isn't just a property of our universe, but a relic of its birth in a higher dimensional arena. Yet the most tantalizing link between string theory and time lies in black holes. String theory suggests that the information swallowed by a black hole isn't truly lost, it's encoded on its event horizon, a holographic ledger written in the language of these extra dimensions. If entropy is about information, and information is tied to higher dimensional physics, then time's arrow might ultimately trace back to how data is stored and shuffled in the cosmos's hidden layers. But there's a catch. Testing these ideas is like trying to read a book sealed inside a locked vault. The extra dimensions are thought to be a billion times smaller than an atom, far beyond our current observational reach. Some physicists hope that future particle colliders or gravitational wave detectors might catch echoes of these dimensions in rare, high-energy events. Others look to the cosmic microwave background for faint imprints of brain collisions from the universe's infancy. What makes string theory so compelling and frustrating is its audacious scope. It doesn't just tweak our understanding of time, it rewrites the stage on which time performs. If proven, it wouldn't merely explain why time flows forward, it would reveal that flow as a shadow of deeper, multidimensional symphonies. Until then, these hidden dimensions remain both a puzzle and a promise. The possibility that time's arrow, like everything else, is just a note in a far grander composition. Life is a rebellion against the universe's slide into chaos, a temporary spark of order in a storm of entropy. Every breath you take, every meal you digest, is a transaction with time's arrow. Your body isn't just subject to entropy, it's a master at exploiting it. Take photosynthesis. Plants capture sunlight, converting disordered energy into structured sugars, a process so efficient it powers nearly all life on Earth. But even this miracle comes at a cost. For every molecule of glucose created, heat dissipates into the environment, nudging the cosmos closer to disorder. Life doesn't defy entropy, it rides its wave, like a surfer carving order from the ocean's relentless chaos. DNA is entropy's most exquisite dance partner. Each time a cell divides, its genetic code copies itself with near-perfect precision, preserving information against randomness. Yet errors creep in, mutations that drive evolution but also reflect entropy's whisper. Aging itself is a testament to this slow unraveling. Telomeres, the protective caps on chromosomes, shorten with each division like a wick burning down. Free radicals gnaw at cellular machinery, and proteins misfold, their once precise arrangements collapsing into chaos. You aren't just growing older, you're embodying the second law of thermodynamics in real time. Even reproduction, life's ultimate cheat code against mortality, plays by entropy's rules. A single fertilized egg divides into trillions of specialized cells, building bodies of staggering complexity. But this order is borrowed, not stolen. The energy required to build a child comes from breaking down food, a process that releases far more disorder than the new life temporarily contains. In the grand ledger of the cosmos, life's brilliance is a local anomaly, a flicker of structure paid for by the universe's growing disorder elsewhere. The irony is profound. The very processes that sustain life accelerate entropy's cosmic victory. Your brain, for instance, is a hotspot of energy consumption, its neurons firing in patterns so complex they give rise to consciousness. Yet every thought, every memory generates heat, dispersing energy into the environment. In a sense, your ability to ponder time's arrow is itself a product of entropy's relentless rise. Some scientists speculate that consciousness might even be an evolutionary adaptation to manage entropy more efficiently, like a captain steering a ship through turbulent seas. Could life exist in a universe where entropy decreases? The math suggests it's possible but bizarre. Organisms in such a world would uneat, expelling perfectly assembled nutrients while absorbing waste. Their memories would consist of future events, their bodies growing younger until they vanished into infancy. It's a fun thought experiment, but it underscores just how deeply life as we know it is entwined with time's one-way flow. From the first replicating molecules to the towering complexity of human civilization, biology doesn't just obey the arrow of time, it amplifies it. Forests grow and decay, species evolve and go extinct, civilizations rise and fall, all contributing to the universe's irreversible slide toward disorder. Yet in this grand narrative, life emerges as entropy's most eloquent storyteller, weaving temporary order into the fabric of time itself, a fleeting but dazzling defiance of the cosmic tide. A housefly dodging your swat isn't just fast, it's living in a different temporal reality. To a fly, your hand moves through molasses, each second stretching like taffy. This isn't magic, it's biology. Smaller animals with faster metabolisms often perceive time in slow motion, their nervous systems processing information at lightning speed. A hummingbird's wings beat 80 times a second, yet it navigates flowers with pinpoint precision. For them, the world unfolds like a movie played at half speed, every detail sharp, every threat avoidable. But what does this mean for time itself? If perception can stretch and compress like rubber, how fixed is time's arrow really? Dive underwater and the rules shift again. Sharks, ancient predators with electroreception, experience time through electrical pulses in the water, a sense we can barely imagine. Their perception isn't just slower or faster, it's layered, like hearing colors or tasting sounds. Even trees, though they lack nervous systems, track time through circadian rhythms and seasonal changes, their growth rings marking years with silent precision. These variations hint at something profound. Time isn't just a universal constant ticking away in the background. It's a fluid experience shaped by the bodies and brains that measure it. Now scale up to the cosmic level. A mayfly lives for a single day, while Greenland sharks swim for centuries. On geological timescales, mountains rise and erode over millions of years, and stars burn for billions. Yet all these clocks, biological, planetary, stellar, are threads in the same tapestry. The universe doesn't care if a fruit fly's life flashes by in weeks or a galaxy spins for eons. Entropy increases regardless, weaving time's arrow through every scale of existence. But here's the kicker: without observers, would time have any meaning at all? A rock doesn't count seconds, a black hole doesn't check its watch. Time's flow emerges from change, and change only matters to those who can witness it. This raises a tantalizing possibility. If consciousness shapes time's subjective experience, could there be alien minds perceiving reality at entirely different speeds? Imagine a species with neural impulses 1,000 times faster than ours, for whom a human heartbeat would feel like a geological epoch, or being so slow that supernovae flicker like fireflies in their night sky. Physics allows it. Entropy doesn't dictate perception, only the direction of change. The universe's clock might be absolute, but how it's felt could be as diverse as life itself. So the next time you miss a buzzing fly or marvel at a centuries-old tortoise, remember, you're not just seeing biology at work, you're glimpsing time's flexibility, a reminder that the arrow we call constant might feel utterly different through another creature's eyes. And somewhere in the cosmos, other minds could be watching stars dance to rhythms we'll never perceive. Ancient civilizations saw time as a great wheel, endlessly turning through seasons, floods, and dynasties. The Mayans calculated celestial cycles with such precision they could predict eclipses centuries in advance, while Hindu scriptures described cosmic cycles lasting trillions of years, universes breathing in and out like slumbering giants. This cyclical view wasn't just poetic, it mirrored the rhythms of nature, where day followed night and crops regrew with each passing year. Even the Norse myth of Ragnarök, where the world is consumed by fire only to be reborn, echoed the certainty of renewal. Time wasn't an arrow but a spiral, folding back on itself in patterns as reliable as the rising sun. The shift to a linear view began with the slow unraveling of entropy's secret. Early clues came from simple observations. Fire reduced wood to ash but never reassembled it. Youth gave way to age without reversal. But the real turning point arrived with the scientific revolution. When Newton defined time as an absolute river flowing uniformly for all, he unknowingly set the stage for a deeper revelation. By the 19th century, physicists like Ludwig Boltzmann showed that heat always flows from hot to cold, a one-way street etched into the fabric of reality. Suddenly, the universe had an expiration date. The idea of eternal return crumbled beneath the weight of thermodynamics. Religion and philosophy mirrored this transformation. Judeo-Christian thought, with its narrative of creation, fall, and redemption, already hinted at linear time, but the industrial age cemented the change. Factories ran on schedules, trains needed timetables, and Darwin's theory of evolution framed life as a march from simplicity to complexity. Progress became the new deity, and time its unyielding conveyor belt. The cycles of harvest and celestial alignment gave way to railroads and telegraph systems where yesterday's innovations made tomorrow's obsolescence inevitable. Yet remnants of the old worldview linger. Farmers still plant by the moon, and cultures worldwide celebrate cyclical festivals like the Chinese New Year or the Hindu Diwali. Even modern physics flirted with cyclicality. Einstein's equations initially allowed for a closed universe that might collapse and rebound, but the discovery of dark energy's relentless push made that vision fade. Now cosmology paints a bleaker portrait, a cosmos expanding forever, its energy diffusing into cold stillness. The cyclical myths of our ancestors were comforting. Our linear timeline offers no such promise of renewal. Perhaps the most poignant difference lies in how we measure meaning. Ancient cultures found purpose in recurrence, the assurance that spring would follow winter, that generations would outlast individuals. We moderns chase progress, racing toward a future we can't rewind. The irony is profound. Our understanding of time's arrow grants us power over nature, yet it also strands us in a universe where every moment is irreplaceable. The past becomes a foreign country, the future a frontier we'll never fully map. The great wheel has shattered, leaving us to walk the tightrope of entropy, one precarious step at a time. Einstein's theory of relativity shattered the illusion of a universal clock. Picture two identical twins. One stays on Earth while the other rockets into space at near light speeds. When the astronaut returns, they've aged less than their Earth-bound sibling. Time didn't just feel slower, it was slower, warped by velocity and gravity's grip. Satellites in orbit experience this daily, their atomic clocks ticking faster than those on the ground, demanding constant corrections to keep GPS accurate. Yet amid this elasticity, entropy's rise remains stubbornly constant. A melting ice cube aboard the International Space Station still drips toward disorder, just like one on your kitchen counter. How can time bend like rubber while entropy marches forward like iron? The secret lies in gravity's dual role. Einstein revealed that gravity isn't just a force, it's the curvature of space-time itself. Massive objects like planets and stars dent this fabric, slowing time nearby like a weight pressing on a trampoline. But entropy doesn't care about these local wrinkles. It's a cosmic accountant tallying disorder across the entire universe. Relativity dictates how fast clocks tick in different places. Entropy dictates which direction they tick for everyone. Think of it like a river flowing downhill. Gravity might alter the speed of the current, creating whirlpools or rapids, but the water never flows uphill. Entropy is that downhill slope, the invisible gradient ensuring time's arrow never reverses, no matter how warped its path becomes. Black holes test this duality to the extreme. Near their event horizons, gravity stretches seconds into eons from an outsider's perspective. Yet for an unfortunate astronaut falling in, time passes normally until spaghettification does its gruesome work. Remarkably, even here, entropy increases. The black hole's surface area, a proxy for its entropy, always grows, swallowing matter and information in a one-way transaction. This marriage of relativity and thermodynamics hints at a deeper truth. While gravity shapes time's flow, entropy chooses its direction. Everyday technologies silently prove this partnership. Atomic clocks on GPS satellites must account for both relativity and thermodynamics. Without corrections, relativistic time dilation would throw navigation off by kilometers daily. But the satellite's power sources, radioactive decay, are governed by entropy's irreversible arrow. The clocks might tick at different rates, but their decay products never reassemble. This harmony between local time warping and global entropy rise is why your phone's map app works, and why you'll never see a shattered windshield spontaneously repair itself, no matter how fast you drive. The universe, it seems, has struck a delicate balance. Gravity and motion may twist time's fabric into knots, but entropy ensures those knots only tighten in one direction. From the quantum flutter of particles to the majestic spiral of galaxies, this interplay crafts the irreversible narrative we call history. Time's relativity lets astronauts OUTP a CE Chinese letter, but entropy guarantees none of us outrun decay. The cosmos dances to both tunes at once, a waltz of flexibility and inevitability, bending without breaking the arrow that binds us all. Quantum entanglement defies every intuition about time and distance. Picture two particles born from the same quantum event, separated by light years of empty space. Change the spin of one, and its twin instantly mirrors that change. No signal, no delay, as if the universe itself skipped the middleman. Einstein famously called this spooky action at a distance, but the real spookiness lies in what it implies about time. If entangled particles communicate faster than light, does that mean they're somehow stepping outside time's usual flow? The key to this puzzle lies in how entanglement challenges causality. In our everyday world, causes always precede effects. A domino falls because another knocked it over. But entangled particles seem to bypass this rule entirely. Their correlation happens instantaneously, with no clear before or after. It's as if time at the quantum level is more like a network of connections than a straight line. Some interpretations suggest these particles aren't truly influencing each other across space, but are instead revealing a pre-existing harmony written into the fabric of reality. A cosmic choreography where time's arrow is just one dancer in a much larger ballet. Experiments only deepen the mystery. In labs worldwide, physicists have split entangled photons and sent them racing in opposite directions. When one's polarization is measured, the other snaps into alignment, even if the decision to measure is made after the particles are already in flight. This delayed choice setup feels like rewriting history retroactively, as if the universe is playing a game of quantum chess where moves can change after the clock expires. The unsettling implication: time might not be the rigid scaffold we imagine, but a fluid construct that can, under the right conditions, fold back on itself. Yet for all its weirdness, entanglement doesn't actually violate time's arrow. No usable information travels faster than light, preventing paradoxes like messaging the past. Instead, entanglement exposes a hidden layer of reality where time and space are interwoven in ways we're only beginning to grasp. Think of it like a pair of synchronized swimmers. Their movements are perfectly matched, but neither is causing the other's motions. They're both following a script written before the performance began. The most radical theories propose that entanglement hints at time's illusory nature. If the past, present, and future are fundamentally connected at the quantum level, then our perception of time as a flowing river might be a trick of scale, like mistaking individual frames for a moving picture. In this view, the universe could be a vast, static tapestry where entanglement stitches together moments that only seem sequential from our limited perspective. What makes this more than philosophy is its potential to reshape technology. Quantum computers leverage entanglement to perform calculations that would take classical machines millennia. If we can harness these non-temporal links, we might unlock new ways to process information, simulate complex systems, or even probe the boundaries of causality itself. The irony is delicious. The same phenomenon that seems to defy time could become our sharpest tool for exploring it. So while entanglement doesn't reverse time's arrow, it frays the edges, showing us a universe where the rules aren't just flexible, they're still being written. Every entangled pair is a whisper from the quantum void, hinting that time, as we know it, might be the tip of an iceberg whose depths we've only begun to fathom. The Novikov self-consistency principle turns time travel from a paradox factory into a cosmic editing room. Imagine stepping into a time machine to prevent your parents from meeting, only to find your every move somehow ensures they still fall in love. Your attempts to erase your own existence keep backfiring. A missed train here, a spilled drink there, all conspiring to preserve the timeline exactly as it was. This isn't fate or luck, it's physics enforcing its own version of narrative logic, like a playwright rewriting scenes to keep the story coherent. At its core, the principle proposed by Russian physicist Igor Novikov argues that any actions taken by a time traveler were always part of history. There's no branching, no alternate realities, just a single, self-correcting loop where cause and effect fold neatly into each other. Think of it like a snake swallowing its own tail. The universe won't allow contradictions, so it tweaks events subtly to maintain consistency. A bullet fired at your grandfather might jam, or your younger self might duck at the last second, not by accident, but because the laws of physics demand it. This idea gets wilder when applied to real-world physics. Quantum mechanics already shows particles retroactively influencing their own past in delayed choice experiments. Novikov's principle scales this up to macroscopic events, suggesting time might have a kind of immune system against paradoxes. Even the tiniest quantum fluctuations could nudge a time traveler's actions toward outcomes that preserve the timeline, like cosmic guardrails keeping history on track. But here's the twist: self-consistency doesn't mean predictability. The universe might allow time travel, but only along paths that don't break causality. You couldn't stop the Titanic from sinking, but you might discover your attempt to warn the crew was the iceberg's first sighting, a closed loop where your interference was always part of the tragedy. This eerie harmony between free will and determinism raises haunting questions. If every time-traveling act is predestined, do we truly have agency, or are we just playing out scripts written in 4 dimensions? The principle also offers a sly solution to entropy's grip. If time travel can't disrupt the overall flow of disorder, only redistribute it within the timeline, then the second law of thermodynamics remains unbroken. A time traveler might bring futuristic technology to the past, but the energy required to power it would have to come from somewhere, balancing the cosmic books. Even in a universe with time machines, entropy's arrow stays ruthlessly consistent, like a bank that never lets you overdraft. Critics argue this makes time travel unbearably dull, a straitjacket of inevitability where every daring plan dissolves into predestination. But supporters counter that it's the ultimate cosmic safeguard, preventing reality from unraveling at the first touch of paradox. After all, if time travel is possible, we'd already see evidence of it in our history. The fact that we don't might mean Novikov's principle has been quietly at work all along, stitching up potential paradoxes before they could fray the fabric of causality. So the next time you fantasize about rewriting history, remember, the universe might be one step ahead, editing your efforts into the very story you're trying to change. Time's arrow doesn't just point forward, it curves back to bite its own tail, ensuring every twist was always part of the tale. Time's irreversible march isn't just a scientific curiosity, it's the invisible hand shaping every story ever told. Think of your favorite film. A hero rises, falls, and ultimately changes. Now hit rewind. the narrative collapses into nonsense, like watching a shattered vase leap back onto its pedestal. This isn't just bad storytelling, it's a violation of time's deepest grammar. From Homer's Odyssey to Pulp Fiction's scrambled chronology, every narrative leans on entropy's rise, even when playing with sequence. Consider the humble three-act structure: beginning, middle, end, a mirror of the universe's own arc from order to chaos. In Macbeth, the titular king's murder of Duncan isn't just a plot point. It's a thermodynamic event, scattering consequences like shards of broken symmetry. Lady Macbeth's famous sleepwalking scene, where she tries to wash imagined blood from her hands, captures entropy's grip. Once the deed is done, there's no undoing the disorder it unleashed. The play's tragic power hinges on time's one-way street, making the past an inescapable weight. Music bends the arrow without breaking it. A symphony builds tension through dissonance before resolving to harmony, mimicking entropy's rise and the fleeting pockets of order we cling to. But here's the catch: you can't unhear a melody. Play a record backward and the Beatles might whisper cryptic messages, but the emotional journey evaporates. Even experimental composers like John Cage, who embraced randomness, relied on time's forward flow to give chaos meaning. Without sequence, music becomes noise, just as without time's arrow, the universe becomes static. Visual art freezes moments, yet secretly dances with entropy. A Renaissance portrait captures a face at one instant, but the cracks in its varnish tell another story. The slow, inevitable decay even masterpieces can't escape. Modern artists like Jackson Pollock weaponized this, dripping paint in patterns so chaotic they couldn't be faked. His works aren't just paintings, they're entropy made visible, their splatters echoing the universe's own messy creativity. Science fiction wrestles with time's arrow most explicitly. 2001, A Space Odyssey's Star Child isn't just an ending. It's a thermodynamic climax where humanity's energy reorganizes into something new. Tenet's time-inverted bullets fascinate because they flout our intuition, yet even there, the plot hinges on irreversible choices. Nolan's characters can't undo the past. They can only weave it into a coherent thread, like cosmic editors stitching paradoxes into the timeline. Why does time's direction feel so universal in art? Because creativity itself is a fight against disorder. A sculptor chips away chaos to reveal form. A novelist wrestles randomness into plot. Every act of creation is a temporary victory over entropy, doomed but beautiful. The stories we tell, the songs we write, the images we craft, they're all echoes of the universe's oldest story. The irreversible drift from symmetry to mess, from potential to history. And just like the cosmos, every masterpiece carries the scars of time's passage, the cracks that let the light in. Eternalism flips our everyday experience of time on its head, proposing that the past, present, and future aren't fleeting moments but fixed points in a vast, unchanging block of reality. Imagine the universe as a colossal book where every event from the Big Bang to the heat death of the cosmos is already written on its pages. Turning the pages gives the illusion of time passing, but in truth, the entire story exists simultaneously. This isn't just poetic metaphor, it's a serious philosophical and scientific stance that Einstein's relativity supports. In his equations, time isn't a river but a dimension, as real and tangible as space. Your birth, your first steps, and every moment yet to come are all equally real, just separated by coordinates in the space-time continuum. But how does this square with time's arrow, the undeniable sense that entropy pushes reality forward? Eternalism doesn't deny the increase of disorder, it reframes it. Think of entropy as a gradient painted across the block universe, rising steadily from the low entropy Big Bang to the far future heat death. The flow we perceive is just our consciousness moving along that gradient, like a train traveling across a landscape that's always been there. The tracks don't move, the train does. In this view, causality isn't about one event causing another in sequence, but about the way events are linked in the geometry of space-time. A lightning strike causes a forest fire not because one happens before the other, but because they're connected in the block's immutable structure. This raises a startling question. If the future is already out there, do we have free will? Eternalism suggests a middle path. Your choices are real, but they're also part of the block's fabric, like a character in a novel making decisions that, from the reader's perspective, are already set in ink. The physicist Brian Greene likens it to a DVD. All the scenes exist at once, but the player's laser determines which moment you experience. Your life isn't predestined in the sense of being fated. It's more that every decision you'll ever make is already a thread in the tapestry. Eternalism also reshapes how we think about history and memory. When you recall your first kiss, you're not conjuring a ghost. You're tapping into a point in the block that's as real as the device in your hand right now. The past hasn't vanished, it's just a place you're not currently occupying. This perspective can be strangely comforting. Lost loved ones aren't gone. Their lives still exist in their own slice of the block, preserved like fossils in the bedrock of reality. Yet the theory isn't without paradoxes. If the future is fixed, how do quantum particles behave probabilistically until observed? Some interpretations reconcile this by suggesting every possible quantum outcome exists in branching threads within the block, a multiverse of alternate realities. Others argue that quantum uncertainty is just an artifact of our limited viewpoint, like seeing only one frame of a film at a time. The block universe might feel alien, but it echoes ancient intuitions. Buddhist philosophy speaks of time as an illusion, while medieval thinkers like Boethius imagined God viewing all of history in a single, timeless glance. Modern physics gives this poetic idea mathematical teeth, showing how relativity weaves space and time into a seamless whole. The tension between eternalism and time's arrow isn't a flaw, it's a reminder that reality might be stranger than our linear minds can grasp. The next time you check your watch, consider this. The seconds ticking away are just landmarks in a landscape that's always been there, waiting for you to explore. Consciousness might be the universe's ultimate timekeeper, not just observing time's passage but actively shaping it. At the heart of this radical idea lies quantum mechanics, where particles exist in ghostly superpositions until measured, collapsing into definite states only when observed. Some theorists propose that human consciousness isn't a passive witness to this process but an active participant, weaving the fabric of time itself through perception. In this view, the ticking clock, the changing seasons, even the irreversible decay of a fallen tree might not exist as we know them without a mind to register their flow. The implications are staggering. If consciousness stitches moments into a coherent timeline, does time unravel in places where no observer treads? Consider the curious case of Schrödinger's cat, trapped in a box where quantum rules leave it simultaneously alive and dead. The act of opening the box of observing forces reality to choose an outcome. Now scale this up. What if the entire universe is like that cat, its history and future suspended in ambiguity until conscious beings like us interact with it? The delayed choice quantum experiments add fuel to this fire, showing that particles can retroactively decide their past behavior based on present observations. It's as if time isn't a fixed river but a flexible tapestry with consciousness pulling the threads taut only where attention is paid. This challenges centuries of scientific orthodoxy. Newton saw time as absolute, Einstein as relative, but both assumed it existed independently of minds. The quantum consciousness hypothesis flips this script, suggesting that without observers, the universe might resemble a frozen hard drive packed with potential but lacking playback. Even entropy's arrow could be entangled with perception. The reason we remember the past but not the future might not be purely thermodynamic, but rooted in how our brains construct narrative from quantum noise. Yet skeptics push back fiercely. If consciousness creates time, why do stars billions of light years away, far beyond any observer's reach, still obey cosmic timelines we can measure? Some reconcile this by proposing that consciousness isn't limited to biological brains, but is a fundamental property of the universe, like gravity or electromagnetism. In this panpsychist view, even a speck of dust might possess a rudimentary form of awareness, ensuring time flows everywhere, however faintly. Others argue that quantum decoherence, the process by which quantum possibilities collapse into classical reality, happens constantly through environmental interactions, no conscious observer required. Time in this framework emerges from countless tiny observations by particles themselves. The debate spills into philosophy's oldest questions. If a tree falls in an empty forest, does it make a sound? Modern physics reframes it. Without a witness, does the tree even fall in a definite sequence? Buddhist and Hindu traditions long held that time is an illusion of the mind, a notion now flirted with by cutting-edge physics. Even our language betrays this link. We speak of passing time as if it's a landscape we move through, yet relativity insists all moments are equally real. Practical experiments remain elusive, but tantalizing clues exist. Patients under psychedelics or deep meditation often report time dissolving entirely, their consciousness unshackled from linear flow. Meanwhile, lab studies show that our brains don't perceive events instantaneously, but stitch sensory inputs into a coherent timeline after slight delays, proof that even ordinary perception is a constructed illusion. Could this construction extend to time itself? Perhaps the truth lies in a middle path. Time may exist objectively, but its flow, the visceral sense of past receding and future approaching, could be consciousness's signature. Like a projector bringing still frames to life, our minds might animate the universe's static block into the dynamic story we experience. Whether this makes us mere spectators or co-creators of reality remains one of science's most provocative mysteries, one that blurs the line between the physics of clocks and the poetry of lived moments. Quantum computers aren't just cracking encryption or simulating molecules, they're rewinding the cosmic clock. In labs from Maryland to Munich, physicists are manipulating qubits to mimic time-reversed environments, coaxing particles to behave as if entropy were running backward. These experiments don't just test theoretical curiosities, they probe whether time's arrow is etched into reality's foundation or merely painted on by our limited perspective. Take Google's quantum processor Sycamore. In a groundbreaking experiment, researchers programmed its qubits to evolve from chaos to order, like watching a shattered wine glass reassemble on its own. By carefully tuning quantum gates, they reversed the usual dispersal of information, effectively creating a pocket where entropy appeared to decrease. The catch: this reversal only lasted microseconds and required meticulous control impossible in the macroscopic world. It's as if the universe allowed them to cheat thermodynamics, but only for a fleeting, quantum-sized moment. Similar breakthroughs are unfolding with trapped ions. At the University of Maryland, scientists used ytterbium ions to simulate a time-reversed version of Maxwell's demon, the famous thought experiment where a hypothetical being sorts fast and slow molecules to seemingly violate the second law. Their quantum demon didn't break physics, it revealed how measurement and feedback can locally reverse entropy's flow, provided energy is constantly pumped in. Think of it like a refrigerator cooling its interior while heating the kitchen. Order is borrowed, not stolen, from the wider system, yet these simulations come with cosmic fine print. While quantum systems can temporarily behave as if time is running backward, the energy required to maintain the illusion always increases entropy elsewhere. This mirrors a profound truth about our universe. You can't reverse time's arrow without paying the disorder tax. Even in these controlled environments, the second law looms like an unshakable shadow, enforcing its one-way rule. The real surprise came when researchers pushed further. By entangling particles across multiple quantum systems, they created scenarios where causality itself seemed flexible. In one experiment, measuring particle A appeared to influence the past state of particle B, as if the present were reaching backward to tweak history. This isn't time travel, but it hints that quantum correlations might blur the line between cause and effect more than we thought. Critics argue these simulations are just mathematical tricks, clever manipulations of quantum states that don't reflect true time reversal. After all, no one's unburning a candle or unscrambling an egg. But supporters counter that these experiments reveal entropy's quantum roots. If time's arrow emerges from countless microscopic interactions, then tweaking those interactions at the smallest scales might let us glimpse the gears behind the cosmic clock. What makes these tests revolutionary isn't just their technical wizardry, it's the philosophical door they kick open. If entropy can be locally reversed, even briefly, does that mean time's direction is more fluid than we imagined? Could a sufficiently advanced civilization engineer regions of space-time where cause and effect run opposite to ours? The equations don't forbid it, but the energy costs would dwarf entire galaxies. For now, these quantum time flips remain lab curiosities, tiny windows into a universe where the rules we take for granted might just be suggestions. As quantum computers grow more powerful, they'll probe even stranger territories, simulating hypothetical universes with different thermodynamic laws, testing whether alternate arrows of time could support complexity like life, or even searching for glitches in our own cosmic code that might reveal deeper layers of reality. Each experiment is a whisper from the edge of physics, suggesting that time, for all its relentless forward motion, might have more secrets left to surrender. The frontiers of time research are stretching beyond anything Einstein imagined, probing realms where the very fabric of causality might fray. At the cutting edge, physicists are wrestling with quantum gravity, the elusive theory meant to marry relativity's cosmic rules with quantum mechanics' subatomic chaos. Picture this: in the vacuum of space, tiny bubbles of spacetime might constantly flicker in and out of existence, each a potential universe with its own arrow of time. Some theories suggest these quantum fluctuations could momentarily bend time's direction, like a river forming tiny eddies that briefly swirl upstream. While we can't yet observe these microscopic time loops, experiments with ultra-precise atomic clocks are hunting for telltale jitters in time's flow at the smallest scales. Meanwhile, the hunt for cosmic clues continues. The James Webb Space Telescope isn't just peering at distant galaxies, it's scanning for anomalies in the early universe's light that might reveal hidden dimensions or gravitational echoes from before the Big Bang. If time's arrow truly began with our universe's low entropy birth, then finding even a single reversed fluctuation in ancient radiation could upend everything. Similarly, pulsars, spinning neutron stars that serve as nature's most accurate clocks, are being monitored for rhythmic disruptions that might hint at gravitational waves from colliding higher dimensional objects, or even defects in spacetime's structure. The boldest experiments aim not just to study time but to manipulate it. Researchers at CERN are simulating microscopic black holes in particle colliders, testing whether information can escape their grasp, a clue to whether time's arrow might be reversible under extreme conditions. In quantum labs, time crystals, structures that oscillate indefinitely without energy input, are proving that certain systems can sidestep entropy's decay, if only in tightly controlled environments. These aren't time machines, but they're teaching us how to carve out pockets where time's rules soften. Yet for all our progress, existential questions loom. If we someday uncover a universe where time flows backward, could we even recognize it as a coherent reality? Consciousness itself seems wired to process cause and effect in one direction. Our brains might literally lack the architecture to perceive reversed causality. And what if time's arrow isn't fundamental at all, but emergent, like temperature arising from atomic motion? In that case, controlling time might be as futile as trying to grab hold of a shadow. The most humbling possibility is that time's direction is the universe's last great constant, a rule so deeply woven into reality that even our most advanced theories can't untangle it. But whether we're on the brink of rewriting physics or merely scratching at its surface, one truth remains: the journey to understand time is also a journey to understand what makes existence possible at all. Every experiment, from the quantum to the cosmic, is another stitch in the tapestry of a mystery that began with the first tick of the cosmic clock. Time's relentless forward march isn't just a feature of our universe, it's the story of existence itself, written in the language of entropy, etched by relativity, and punctuated by quantum enigmas. From the unimaginably ordered spark of the Big Bang to the chaotic maw of black holes, we've traced the arc of time's arrow, watching as disorder rises like an unstoppable tide. But for all we've uncovered, the mysteries only deepen. Could there be corners of reality where time runs backward, or loops in on itself like an Ouroboros swallowing its tail? The equations of physics don't forbid it, yet our lived experience insists time is a one-way street. This tension between theory and perception is where the magic happens. Relativity bends time like rubber, quantum mechanics frays its edges, and entropy locks its direction, but consciousness might be the silent conductor orchestrating the whole symphony. Without minds to witness it, would time's flow even have meaning? Ancient civilizations saw time as a wheel, Einstein framed it as a block, and modern physics suggests it might be an illusion woven from countless quantum threads. The truth could be stranger than all these visions combined. What's clear is that time's arrow isn't just a scientific curiosity, it's the invisible scaffold of our lives. Every memory we cherish, every plan we make, every heartbeat and sunset exists because entropy's rise carves the past from the future. Even our art, our stories, and our technologies are love letters to time's irreversibility, attempts to capture fleeting moments in a universe that never looks back. As we stand on the brink of discoveries, quantum computers simulating reversed time, telescopes probing the Big Bang's echoes, experiments testing the fabric of causality, we're not just observers. We're participants in time's grand experiment, riding its arrow toward uncharted horizons. So while the cosmos keeps its secrets for now, here's what we know: this moment, right now, is a singularity of possibility. The past is set, the future is unwritten, and the present, this breath, this thought, is the only slice of time we can truly call our own. If this journey through time's mysteries sparked your curiosity, let's keep the conversation going. Hit like, subscribe, and drop your wildest theories in the comments. What fascinates you most about time's arrow? Could we ever bend it, or is its direction the universe's ultimate law? Until next time, remember, the clock is ticking, but the story is